Okay, we are gonna do the steady state model of an induction machine, and we are gonna continue with our squirrel cage induction machine. So here we have the voltage on each phase and the current on each phase. So before we figure out that our phasor Bs alpha beta was equals to our uh, alpha component plus J and our beta component. And we also figured out that this was equals to 3 halves of the peak voltage, uh, multiplying cos of omega st plus j. So this was our alpha component, and here we have our beta component. It's going to be 3 half bm sine of omega st. So we can say that this is 3 halves bm cos omega st plus j sine omega st, and we can use here an identity to get that our bs alpha beta is equals to 3 halves bm e to the j omega st. And now we can also say that bm is equals to I'm sorry, I'm gonna say that bs is gonna be bm multiplying an angle of 0. That is what we got here. So we can write this alpha beta is equals to 3 halves bs e to the j omega st. Okay, now we are gonna do the same for our current. So we have is alpha beta equals to 3 halves im cos of omega st, but we have to subtract an angle here. This is the angle of phase shift of the current plus j 3 halves im cos of omega st minus theta. So this is our alpha component and this is our beta component. And we figured out this in another video. So we can collect our terms here. So we are gonna get our is equals to 3 halves im e to the j omega st minus theta. And we know that this is the same that having 3 halves im e to the minus j theta times e to the j omega st. And we are gonna say that I capital is equals to im e to the minus j theta. So we are gonna have here that our is gonna be equals to 3 halves I capital S multiplying e to the j omega st. Okay, and now we need to do the same for our IR. So we know that IR is equals to IS multiplying minus an angle, epsilon. This is another thing that we figured out in another video. So now we can apply this and say that IR is equals to 3 halves IM e to the j omega st minus theta. That's what we had here before for is. And we multiply this by our angle minus je. So we are going to have that our IR is equals to 3 halves. And again, we are going to say that IM is equals to, I'm sorry, capital IR is equals to IM multiplying e to the minus j theta. Okay, so here we have omega st minus theta minus j omega. So if we apply the same identity that we did here, we can separate it. So we are going to have this here. So IR, and the terms that are left is e to the j omega st. Okay, let me move this down. Omega st. Now, in another video, we figured out that epsilon is equals to omega rt. So this is the angle between the faces. I'm just gonna give a quick explanation here. So here we have our alpha beta component in our, here we have our alpha beta component in our rotor, in our stator, I'm sorry. So alpha s, beta s, and here we have our alpha beta component in our, well, I don't know why I'm drawing the inductors, but just to, as an illustration. So we have alpha in the rotor and beta in the rotor. So this angle between both of them is epsilon, and this is the angle between them. So if we derive epsilon with respect to t, this is an angle, so we will get our angular speed, WR, because this is the speed in which R is moving. So that's why we get here this. Okay, so minus omega RT. Okay, so I'm just gonna write it. I'm gonna factor out the t. So we are gonna have omega s minus omega RT, omega R times t. Okay, so now we have our three equations. We got our BS here. We have our IS here. Our IS here. And we have IR here. Okay, so remember all of these are vectors. Okay, so we can go back here to our original equation. How is this? And plug the values. So we are going to have this equals to R1 times IS, that is this, plus R0 di dt of IR, that is this, times e to the j epsilon, and remember epsilon is omega rt. Okay, so we need to, wait, did I miss one? Yes. Maybe make it smaller to make a space. I missed the term for L1. So we have here plus L1 didt times is, and is is all of this. Okay, now we have the third terms R1, L1, and L0. Okay. So now I'm just gonna move some terms. We need to figure out those derivatives. So we're still gonna have this here. We can't do much right now with it. So we are gonna have plus L1. We can take out the 3 halves, and we can take out the is. So we are gonna have the derivative of e j omega st. Okay, and for the other one, we're gonna have again 3 halves L naught ir, and the derivative of, okay, so we look here, we have omega rt minus omega rt plus omega rt, so this one and this one can go, and we will left with omega j omega s. So j omega s. Okay, so we are gonna still have this. This one doesn't want to copy. Okay, so we're gonna have this. R1 3 halves is. Okay, we can just expand this 3 halves is e to the j omega st. We're gonna have plus all of this. Now the derivative of this is j omega s times e to the j omega st. And similarly for this, we're gonna have practically the same. I don't know why it doesn't want to copy the whole thing. dt. But here we're gonna have j omega s. Forgot to write it here. This is omega st. Okay. So, but without the derivative because we just did it. Okay. So now we can see that all the terms have 3 half and j omega st. So we can get rid of all of them. So we're gonna have half bs r1 is plus L1, I'm gonna have plus j omega s here, L1 is, yes, plus j omega s L naught ir. And like this we have our steady state equation voltage for our stator. So we can start drawing our circuit. What is gonna look like. So here we're gonna have our BS. We are gonna have an R1, and our current Is is moving here, so we have this term. Now we have omega s L1. So we are gonna have here omega s L1 is an inductance here. Let me write it a little bit better. And this is our L1. And Is is moving through it. And we have omega s L naught and another current. So here we're gonna have another current IR that is adding with Is and is going through an other inductance L naught. Okay, so like this we have our first part. Now we need to figure out our equation our for our rotor. So what can we say about rotor? Our equation of a rotor is that it's a squirrel cage, so the voltage should be 0. So we have 0 equals to R2. Well, now I'm just gonna rewrite the equation that we have up there. R2 di dt IR plus L naught di dt Is e to the minus Ke epsilon. Okay, so again, we just need to, we know what are R, we know our values of our currents. We just figure out, and we know that epsilon is omega RT. So we are gonna get that 0 is equals to R2 that multiplies IR, that is all of this, plus L2 that multiplies the derivative of IR plus L naught the dt that multiplies Is, well, the derivative of Is times e to the minus e, I'm just gonna write omega RT. So again, we can collect terms. So we have 0, 3 halves R2 IR to the j omega s minus omega RT plus 3 halves L2 IR and the derivative of, just gonna copy it, this plus 3 halves L naught Is and the derivative. So this is the same that having e to the j omega s minus omega r times t. Okay, so now we do the derivatives. So we are not here, we're gonna get this plus 3 halves L2 IR, and the derivative of this is gonna be j omega s minus, let me write it together so it doesn't, j omega s minus omega r multiplying e to the j omega s minus omega r t. Okay, and down here we're gonna have 3 halves r naught is j, we're gonna have the same than this, so just gonna paste it here. Okay, so now we see that we have 3 halves j omega s minus omega r t in each term, so we can get rid of all of them. So we're gonna have 0 equals to R2 IR plus L2, so J L2 IR omega S minus omega R plus J L2 IR times omega S minus omega R. Now, we know that in a previous video we figured out that J omega S minus omega R was our slip speed. That's omega S, omega R. And our slip is equals to omega S minus omega R over omega S. So if we invert this, we say 1 over S, we are gonna get omega S over omega S minus omega R. And I'm dividing X, this is X, our slip. We're putting 1 over our slip because here we need to get rid of these terms. So if we multiply this whole thing by 1 over S, 1 over our slip, we are gonna get 0 equals to omega S minus omega R, R1 IR plus J L2 IR times omega S. Now let me write it in a, because we know that this J has to go with our omega S. So let me write it better. You know that we are gonna have J omega S R2 IS, that's better, plus J omega S R0 IR. We can go a little bit further and say that this is 1 over our slip, so we can have here R1 over slip equals to times R plus all of this. And like this, we have our second equation. This is our equation for our voltage in our rotor. So we have our equation for voltage in the rotor, and we have our equation for our voltage in the stator. We can paste it here, both equations. So now we can complete the circuit. We have IR times, well, let's look here, L2 times, oh, this is IS. Then I changed the terms here. I wasn't looking up, so I inverted the terms. L2 is IR and this is IS. It makes sense because this is the mutual inductance. So it has to multiply by our IS. Okay? Now it makes sense because here we have our L2 that multiplies our IR. Okay? And here we are gonna have our R2, this is R2. That's, I wasn't looking up when I wrote this equation, that's why I messed up some of the terms. R2 over our slip. And here we have our omega S R0 times IR. That is this one. So, okay, this is our model of our squirrel cage induction machine in steady state.